how increasing the size of your data set improves your classification accuracy. They said, let's say you have 1 million labeled pictures, they got 40% accuracy. 10 million, 50%. 100 million, 60%. 1 billion, 70%. 2 billion, which was their max, 70-something%. My personal opinion, that was kind of their self-promotion, like, ooh, look at us, we have 2 billion labeled data images, which nobody else in the world has. So that's why companies like Google, Facebook, and so on are very comfortable open sourcing their tools, the TensorFlows and so on, because the tool is useless without the data. So they feel comfortable saying, here's what we used, now apply it to your own data, and good luck getting our data set size. But if you can, you'll easily get the same results. Nothing really magical about that. So now that we know what it is, how to use it? Machine learning has two parts. There's training and inference. Training is taking your data, building this model. Once you have the model, now you want to use the model, how to get its predictions. That's called inference. So you take your data and say, please infer some prediction based on this data. This is the extent of my Google Sheets skills, so I apologize for the lines aren't so pretty. So first you start off, the top half is basically beforehand data capture. You might have multiple sources of data that you kind of have to put together. For example, without loss of generality, an Amazon purchase prediction engine. You might have purchase history, you might have viewing history, you might have affiliate data from other sites. And you put it all together and you say, okay, this is the same user, and this is their purchase history, this is there. You aggregate it all together, store it in a large database. Now your data is saved, and it's there in the database. Fine. Now the user logs into Amazon.com, and you want to show them predictions. The front-end service says, okay, user number so-and-so logged in. No, tell me what to show. Make a request to the backend API, which now has to do some predictions. It calls the inference server. First, it takes data and converts it into all the machine learning stuff, which we'll talk about in a little bit. And once it gets all the stuff in the right format and everything's all together, it calls model.predict. That's actually the one line you type, model.predict, and you pass it the input data. Once it gets it, you get its predictions, which is just a bunch of numbers. You have to convert that into something reasonable and then assemble that with some of the data. For example, if it's a bunch of products, you might have to get the names and titles and the pictures and the prices and so on, send it back to your backend API, send it back to the front end. Now you have your fancy schmancy predictions. So as we started in the beginning, model.predict is an important piece of this. The whole thing wouldn't work without it, but it's just one small piece of this giant pipeline. Now, where did that model come from? How did it get trained? Am I doing on time, by the way? Am I speeding through? But how did it get trained? Where did it come from? So this is a typical machine learning training pipeline. At some point, I got tired of drawing all the lines in here. So there's lines all throughout here. And it's not always linear. There's cyclic because you have to go back and get more data, and you realize this data was wrong, and so on. So data capture, for example, for computer vision. Let's say you want to make a dog versus cat classifier. So you go on Twitter or Flickr, and you look up Creative Commons license, so you can use it for commercial purposes. All the pictures labeled dog, cat. And then you realize that, let's say you want to find out where they are in the picture. So you need bounding boxes, you need annotations, and you go on Mechanical Turk. I had a cool story about Mechanical Turk, man. In the 1600s, there was a wooden robot that was very good at playing chess. And nobody knew how this wooden robot was playing chess for, I think, 100 years, until somebody realized there was a small Turkish guy inside moving the robot. So Amazon now has a product called Mechanical Turk, where you think you give it data and it'll label your data, does amazing stuff. It's really people, it's really workers, and they pay them a couple pennies or a couple dollars per task, and you get your amazing results back. So anytime you hear the idea that something Mechanical Turk, or there's a lot of competitors now also, or also called human in the loop, where you have an amazing system, does amazing stuff, but really it's people running the whole thing. So you have to tag it, and usually people aren't so accurate, so you have to clean up the data, make sure your labels are good. If your labels are messed up, then your quality of your model suffers. That's what we deal with a lot today, is that users will sometimes tag the wrong thing. And sometimes what we'll do is actually a company that specializes in this. They send your data to several taggers, and they'll kind of rank them, vote them amongst each other, and figure out which tagger is the most reliable, and try to automatically determine which are the bad tags. Then Google just sent an email. They have a beta product of automatic bad label detection. It's a whole big thing. Fine, let's say you have your data set is ready. Now you need a machine to train this on. So you do your GPUs and your CPUs. There's actual articles about building a machine learning computer. You need these GPUs, you need the CPU, how much RAM, and how this. Fine. Software is set up. Well, what kind of drivers? What kind of do you want TensorFlow? Do you need Caffe? Do you need C++? What do you need? Environment setup. We have a machine learning engineer at my company. He's a great guy. He's great at machine learning. He reads papers all day. He'll implement the latest and greatest models. And he only codes in a Jupyter notebook. That's basically it. So you have to set up his Jupyter notebook and access and environments and drivers and so on. That's all set up. Great. Now the data is in a database. So he'll ask me, can you please write me a SQL query to extract all this data? Fine. And I'll use pictures. Can you copy the pictures to my machine because I don't know how to access them? Fine. Now you have your pictures. Let's say you have 100,000 pictures of dogs and cats, but you really want 1 million pictures of dogs and cats. So how do you get more pictures without actually getting more pictures? It's a thing called data augmentation, where you say you vary the brightness a little up, a little bit down, vary the contrast a little bit up, a little bit down, you rotate a little right, a little bit left, and you flip it, and now you have 54 times as many pictures as you had before, suddenly, with just a few little computer vision tricks. You want to store your augmented data because augmentation takes a lot of time, a lot of processing, so you want to store your augmented data. Then model coding, you want to figure out which model you want to use. Just pick one and basically code it via the inputs, via the outputs, how many layers, which layers, and so on. Data training versus validation versus test. The idea is the following. Let's say you have 1 million labeled pictures. You don't want to train on all your 1 million pictures because then you don't know how well it actually did. And it's also possible that the model will just memorize all the 1 million pictures and it won't be able to tell you anything about any future pictures. So to prevent that, data is often split into training, validation, and test. A split, for example, might be 70% for training. That's what your model actually trains on. 20% for validation. And during training, your model will try to use the 70% that it has to make the other 20% as good as it can. So it trains on these such that its goal metric is the other 20% that it hasn't seen yet. You save 10% for test as a final validation that your model didn't just memorize the validation data. And you want to save this so that next time you don't actually randomly resplit in a different way and you retrain your model and now it's better just because the training data happened to have split a little bit better. Well, there is a way to use that intentionally. It's called an ensemble, where you train the model 5 times on different splits and take toolchain initialization. TensorFlow, for example, is very happy to work on CPUs or GPUs or Google's new TPUs. Really, the TPU is just a matrix multiplication in hardware. But they say, oh, it's a tensor processor. It is very good, don't get me wrong, but I don't think it's as fancy as they make it out to be. And you want to make, so if your GPU drivers aren't running correctly, TensorFlow will oftentimes, by default, silently work on the CPU instead. So your performance will plummet and your service is going to be slow. You're not going to know why. And it's because your GPU driver didn't initialize this particular time. So fine. Data transformation, oftentimes, for example, this image classification doesn't work on arbitrary size pictures. Sometimes it'll work on only square pictures. You have to crop it or resize it or something like that. You want to save these so that you don't have to rerun it again every time you retrain. Learning rate configuration. Neural networks often have a lot of parameters. So many that there's a whole new thing called hyperparameter tuning is a whole field. And Google wrote a paper recently called Model Parameter Search, where basically they trained the same model, which takes a week to train, and they trained about 100,000 of these with different parameters, and they found the best one. So somebody said that doing that, use as much carbon dioxide as 5 cars will in their entire lifetimes. So specifying what the parameters are, and learning rate is one of the parameters, how fast the descent goes. It's not just a number. It's based on what iterations and what your current loss is. It's a whole small little algorithm of figuring out what the learning rate is. Fine. Put all this together, and now you literally write model.train. It's literally one line. Give it your test data, your training set, and your validation set, and then model.train, and wait a couple hours. Usually give you some nice output about what it's doing. There's another product besides TensorFlow. There's TensorBoard, which gives you nice little graphs of how your validation is doing and all the fancy stuff, every layer, like that. Now the model is trained. Now you have to figure out, at the end, your model gives you numbers, 4, 5, 6, and so on. You have to know what they mean. So 4 is a toaster, 5 is a refrigerator, and so on. You have to save that somewhere. Inference validation, now you run this model on your validation set, your test set to see how well it actually did. You have to save this model somewhere. One thing I'm dealing with now is that Keras, which is a wrapper around TensorFlow, serializes its models using Marshall rather than Pickle. And Marshall isn't compatible across even minor Python revisions. We're trying to switch from Python 2 to Python 3 because Python 2 is getting deprecated soon. So we have to rebuild all our whole thing in Python 3 because our existing models won't load in Python 3 because, fine, that's model saving is the whole headache. Model upload, you have to save it somewhere. It's on your machine learning machine. Now you want to put it in the cloud, you put it on a specific service somewhere, where, and so on. Scaling vector, let's say your input data as part of your training, you decide the average picture is too bright or too dark. So what's very often you'll subtract the mean of all your images from the images, so all the images start at 0. You have to save that subtraction. There's scaling vectors and so on. Metadata, you want to save all the things I'll talk about in a minute. Parameter, what data the model was trained on, for who, and so on. Save that, put it somewhere legitimate. Save your training validation so that next time it's ready, it's the same thing, result display, so you can draw little pretty graphs about area under the curve and false negative rate, false positive rate, and so on and so forth. Fine. Now that you have your model and it's saved somewhere, a bunch of organizational issues. For example, if you have a bunch of customers, what customer was it trained for? If you have a bunch of products, you want to make sure that when you're loading for the right one. What data was it trained on? For example, your boss comes to you and says, this prediction engine never predicts a toaster, even if I'm looking at toasters. Why not? You say, oh, well, there was no toasters in our test data, so that's why I didn't predict on it. So you want to know what you trained on, and how many it was of each one, and so on. Which inputs does it need? For example, the model just takes numbers. You have to know what the numbers mean. So does it need the picture, cropped, what size, and so on. What do the outputs represent? Let's say output 4 is a toaster, output 5 is a refrigerator, and so on. You have to save that somewhere and load it and have it be usable by your other APIs. What revision is? Let's say you train a better version of your model, or you think it's better because the accuracy reported was higher. We'll talk about it in a minute. You have to be able to load previous revisions if the new one's not as good, and so on. What dependencies does it have? Oftentimes, the neural networks will need certain types of layers. Some are provided by the architecture. Some of them you coded yourself. For example, one we coded based on a paper was called Prelude, Parametric Rectified Linear Unit. And that's not available in the standard TensorFlow, so we coded it. And the model relies on it. So when you run inference, that layer has to be available and provided in inference. And different revisions of the model have different layers and so on. Even worse, you might have the same layer name might have different structures. So you have to make sure it's the right structure, the right layers, and so on. What compute resources does it use? TPUs, GPUs, and so on. Some models might be small enough to run on a CPU until it gets too big, and that's run on a GPU, and you have to load it, and it has to be met. Where is it stored? Is it stored in S3? Is it stored on local disk, or is it network somewhere? And how do you pull it? How do you load it? Live or experimental? Oh, Hashem should help you if you try to do this whole thing, but not push it to production, just so you can test it out. This whole thing over here, you have to build a copy of this for your test data. So in my company, we actually have a new backend server, a new front-end server, and a separate inference server, which loads different models that you go to the dev version of the website, you'll see different models. It's a little bit of a pain to set up and making sure they don't cross and so on. So to solve this, companies have realized this is a problem, and they saw a business opportunity. So Google Cloud, AWS, and I'm sure Azure and others will provide, as part of their toolkit, model organization, model running. You give us the model and we'll run it, we'll do inference, we'll do versioning, we'll do all this fancy stuff. I get emails from startups that saying, oh, we will manage your models for you. Just give us your models, and for a couple dollars a model, a couple cents for inference, whatever it is, we'll take care of everything. Some companies decide to build it in-house. Uber's been pushing their machine learning abilities recently, so they have their internal only tool called Michelangelo, which does all this fancy stuff. They have some related tools that are open source, but this is kind of one of the organizational issues you'll see. It's very common. So let's say somebody actually wants to add machine learning to their company. You have a product, it works, but you want to sprinkle some machine learning on top, right? So how do you start? I don't recommend you actually start with the whole pipeline from the beginning. Honestly, my first guess would be Google Analytics. It's been around for a long time. It does a lot of this stuff, and it can actually get you pretty good insights. For example, Marissa Mayer, who used to be the face of Google, now she's the CEO of Yahoo, said back in the day they were testing which shade of blue is the best type of blue for the links on the ads or something like that. And they couldn't figure out which one. So they tested it. They tested 41 different shades of blue to find out which one would be the best. I'm not sure if this quote from Bing is about Google's blue or their own. I'm sure Bing did similar experiments, but the blue that they found was worth, they say, $80 million because the change of click-through rate might be from like 0.2 to 0.23, and that 0.03% over billions of clicks might be very valuable. And Google Analytics will do that kind of stuff for you. You can do A/B testing, you can do automatic, and you can show you results and show you little flows and little graphs. It's not that hard to set up, and if you, with the right bits here and there are other A/B testing platforms also that will give you pretty good insights. You can make users happier and get all this good stuff. Format data appropriately. So one of the important things is I saw in one of the graphs, there's data capture, all have to be going to the same place. If you have data on database here, and let's say in JSON format here, and YAML files here, and on a spreadsheet here, it's going to be very difficult to run a simple machine learning model on those because every time you have to load all that data. So the best thing I would recommend is aggregate it all into one place. Once it's all in one place, then it's very simple to run a machine learning on provided, readily available data. Don't pre-filter your data. There was the talk I heard once in 2007. I tried to find it for this. I didn't have time. Rather, I didn't start early enough to prepare for this. And a guy from San Diego National Labs was talking about machine learning and forested trees and so on. One of the anecdotes he gave was UPS wanted to know what's the most important factor that determines whether a package will be damaged during shipment or not. So is it size, is it weight, is it distance, is it air, freight, and so on. One of the pieces they happened to have available was the origin zip code. So they plugged everything together, said model.fit, or this is before TensorFlow did its statistical regression, and they found the single most important factor was the origin zip code. As, I guess I gave it away here. There was some factory in middle of nowhere, North Dakota or something, that wasn't packaging their fragile items very well. And a lot of users were complaining that, hey, my item didn't arrive intact, and UPS thought it was their fault. It turns out they just weren't being packaged well. So a little bit of insight, taking all your data and run a little model can get you big savings. Don't make assumptions. This is from a story in Freakonomics, great book. They talk about similar issues. And this is about a daycare center in Haifa where some of the parents were picking up their children late, and it cost them expenses because the teachers had to stay late and so on. So they said, here's what we're going to try. We're going to impose a 10 shekel fine. They said $3, I'm assuming it was 10 shekels, for anybody who picks up their kids 10 minutes late or more, hoping to bring down the number of late pickups. So they implemented this, and they look at the data, and it turns out the number of late pickups promptly went up. Well, the reasoning they assume in the book is that before there was a moral incentive to pick up your kids on time. You feel bad. It's typical Jewish guilt making teachers stay late. For 10 shekels that can buy away that guilt, it's great, it's a bargain. So having the data that you have available, and don't make any, next slide is going to be don't make assumptions, you can get pretty good insights. Numbers have no type. This is an important point. There's 3 different points in here. The computer doesn't actually understand what it's doing. It doesn't reason, doesn't think. It might look like it, but it's all a facade. It's really just numbers. So the question is, what do the numbers represent in the real world? How do you interact with it? So we'll start on the right. This is Google Photos, very nifty little tool. Will tell you what's pictures of, where it was taken, and so on. And one person kind of complained that, hey, this is not a gorilla. Once they posted this on Twitter, it took Google a couple hours to fix it. Their fix was to remove the gorilla's category entirely, to the point where if you go to the zoo and take a picture of a gorilla, it won't show up as a gorilla because they had too many false positives in this field. That's one way of doing it. The computer doesn't know. It fits. The data regressions, the match, that the pixels are nice. So it worked. So understanding what the data means is important. This one on the left is from a screenshot from a documentary from 2005 by PBS called The Great Robot Race, about the DARPA Grand Challenge. The government spent billions of dollars trying to build self-driving cars. And they got not so far at all. So they said, okay, new idea, $1 million grand prize for anybody who can do this for us. And a bunch of teams entered, spent $7 million of their own money for the $1 million grand prize. But in 2004, nobody did it. In 2005, 5 teams were able to finish a 132-mile desert course autonomously. This is from the winner, Stanley, from Stanford's Artificial AI Lab, run by a guy named Sebastian Thrun. So their big idea was sensor fusion. There's a laser which clears a path in front of the car for a short distance, about 20 meters. That's good enough to go up to 25 miles an hour because they could stop in time if they see an obstruction. To go farther than that, it uses camera. And what it's doing is it takes the part of the picture that was already cleared by the lasers, say this part over here, was already marked as drivable, and the camera tries to find similar pixels in the picture that it's going to assume is also drivable. So the area marked as red is similar in contrast and color and so on to the part that is drivable. So if it's driving on paved roads or desert roads and so on, it'll adapt. It doesn't actually understand what it's doing. In the presentation that the guy gave, he said, we tried a different model that tried non-drivable versus drivable. The problem was sometimes it would mark the sky as drivable and other lakes and things like that. Big problem. If you look on the picture over here, there's part of the hood over here that's in red. It's also being marked as drivable. The algorithm doesn't understand what it's doing. It's just trying to fit the regression to find the most similarities. It doesn't actually understand what it's doing. This picture over here is from a joke my high school physics teacher told me. He said a student runs up to his professor and says, "Professor, we just got back the results from the electron mass spectrometry experiment. What does it represent?" The professor says, "Well, what are the axes?" He says, "Oh, this is mass and this is electron velocity." And he says, "Oh, well, it's very simple because as mass increases, you get more impact and impulse and so on. But as you go too big, then the accelerator doesn't have enough power, and that's why it shapes off." He says, "Oh, thank you very much. Oh, I'm sorry, I messed up the axis. This is velocity, that's mass." He says, "Oh, no problem. That's because it resonates over here, and after it stops resonating, that's why we have the square diversion over there. So no problem. You can explain anything." The point is, this is just a bunch of numbers. They don't really represent anything until you give it meaning. Careful about making deductions. There's an excellent book called How to Lie with Statistics. It's from 70 years ago. It's still relevant. A lot of interesting stories in there that are very practical in this kind of field. One that I'll give a personal story. I was looking into dorms at MIT, and they said, okay, we have half of our dorms have one person per room, half of our dorms have two people per room. You think, great, half the dorms are one person, half the dorms are two people, so you think I have a 50-50 chance of getting a single room. Well, that's not the case. You have a 1 in 3 chance of getting a single room, because 2/3 chance you're getting a double room versus the single room. So the data is correct, it's there, it is what it is. They're not trying to lie, but what you infer could be very different. So you can make the numbers represent whatever you want based on how you look at the same data, but just twist it a little bit and you get different things. Just think about it now, there was also one of the things they talk about is axes. It's very common, you'll see this in journalism also, where they'll zoom in on a very small range of a graph, for example, and it looks like, oh, the economy is going down like crazy, really down 1%. They zoomed in on the 78 to 77%. It looks like it's down 100%, but really it's not a big change at all. So it's the same numbers. If you look at the axes carefully, you'll see this is what it is, but they're trying to impact a certain message. And it's very easy to change what message you want to impact just based on how you explain the numbers. Also, models self-reported versus real-world accuracy. Models can be used in different ways. For example, let's say you have a typical classifier. So this is a dog, this is a cat, great. And it says, oh, based on my test set, I'm accurate 98.2% of the time. Fine. But what if the way it's actually used is a little bit different? For example, in Google search, for example, being on the first page is considered a win because it's one of the top 10 results. Being third or second is awesome. If the person was looking for the link that you showed second, that's actually pretty good of the whole internet. But let's say you're doing Google voice recognition. They would say being second is nothing. You have to be first, because if the right word didn't come up, then the person would assume it failed. The fact that, oh, I got in the top prediction doesn't matter. So being accurate in that the model is used in the way that its accuracy is reported is very important. Otherwise, your accuracy doesn't mean anything. That's another example that happens all the time. So oftentimes, being cognizant of this, I'll do searches in incognito mode. And I'll say, "What are you in incognito mode for?" I said, "I don't need this kind of stuff in my history. I don't want to pop up every time." Fine. Q&A. Shameless plug. Before then, I volunteer for Lakewood Chaverim. I do some of the tech support. Well, pictures didn't come up. I built the Slack bot. That message comes in, goes all to the dispatchers. They can reply by clicking on an emoji. Sends a text message to the call that's on the way, and so on and so forth. We're all busy. I'm also busy. If anybody wants to volunteer their time to help us out, Slack me.
Is that text input by the dispatcher, or does it have
What's actually it's entered. They enter ###, which is a new message, and then just the middle part of the message. Actually, there's two programmers from Lakewood built a dispatch app which integrates into this. It does the automatic addressing. So this is a Google Maps link. This is a clickable phone number. Waze and iOS links, so that if you have whatever platform you use, it'll do that kind of stuff. Probably should blurt out some of the privacy stuff. So.
But someone has to translate the audio into.
No, so this is typed by the dispatchers, and that's kind of it. The end. Any questions? My mashgiach used to say Q&A is his favorite type of shir to give because he doesn't have to prepare. If I know the answer, I know the answer. So Q&A is.